Here we'll cover the best practices for the proper setup, mesh, run, and we'll also take a look at the post-processing of this wing under subsonic flow conditions. We'll also cover how to change the wing design and run a new analysis. In our other video, we showed how to build the geometry of a wing within STAR-CCM+, which is then fed directly into the simulation workflow. To see how this geometry was built, please see the link below. The wing built in that video can be changed in terms of pitch at various points in the wing length, the sweep, the height and or length scaling of each airfoil profile at various points in the wingspan, and the degree of wing dihedral or anhedral. The wing being used in this case is arbitrary, but is similar in size to an RC aircraft with a wingspan of 4.5 feet. I should mention that you can import geometry from other CAD packages. You can import the geometry, set up the sim, mesh it, run, and swap out geometry for different design iterations. Or instead of swapping out parts, you can directly link into that software to pass geometry directly between CAD and STAR-CCM+. But for the purposes of this video, we operate solely within STAR-CCM+, since this removes the need to swap out geometry and set up a link to another package. To see how to swap out geometry parts, see our other video tutorial in the link below. I did have to make some changes to the geometry for this simulation. The overall setup remained the same as seen in the previous video, but I changed the following parameters for the transformed sketch planes. And then further along in the process, I also changed the scaling as seen here. After this, I created a loft between face sketch 1 through 7, and then I also created another loft between face sketch 7 through 10. Those can be seen here. I also had to change the shape of my domain. If I go into sketch 1, select edit, you can see here if I zoom out that the shape of my domain represents something that looks like a bullet. This domain shape is better suited for subsonic flow. I also named these two faces inlet, and then this downstream face outlet. And then finally, at the very end of my process, I had to scale everything down in size, so that instead of working in meters, I was working in feet. The final step in the first video was to transfer the wing bodies and the domain body down to a parts level. This can be done by selecting our two wing bodies and our domain, right-clicking, and selecting New Geometry Part. Now in the parts listing, you can see all three of our bodies. Then under Operations, I'll right-click, go to New, and select Subtract. This will allow me to subtract the two wing bodies from the domain. I'll expand Operations, and when I select Subtract, the target part should be Body 13. Then I can right-click on this and select Execute. This gives us one final volume or part to work with. To briefly explain what the parts level is, when we transitioned each CAD body to a part, we tessellated the surface of our solid CAD body. Here in the scene you can see the tessellation or triangulated faces that make up our part. So each part will contain a set of surfaces, and each of those surfaces will contain a set of triangular faces. In the parts level we can manipulate faces, organize them into different surfaces, and can clean each part surface of any errors. Because we have organized our surfaces already at the CAD level, and the geometry is clean of any surface errors, we can transfer this part to Regions. Regions is focused on CFD, where we can apply physics and mesh. To do this, I'll right-click Subtract and select Assign Parts to Regions. Here I'll select Create one boundary for each part surface, and then create a feature curve for each part curve. I'll select Apply and Close. Now if I scroll down, you can see under the Regions node, this is now populated. But before moving to Regions, I'll condense this, and I'll also condense Geometry. Our Geometry node is complete, so I'll then move on to Continua. I'll begin by right-clicking Continua, select New, and Physics Continuum. Then I'll right-click, select Models, I'll select 3D, Steady, Gas, Segregated Flow, Constant Density, Turbulent. And notice that because Auto-Select Recommended Models is on, it selected RANs for turbulence. Here we would consider either Spilart or K-Omega SST. K-Omega SST is typically preferred. It is robust, behaves well near walls, and does well in recirculation regions, such as bluff body protrusions, base drag, and so on. Either low Y plus or all Y plus, and I'll cover what this means in a moment. Boundary treatments can be used with this model. This model works best when complex geometric protrusions exist, bluff body separation occurs, and at supersonic speeds. The Spilart turbulence model may be used in cases of streamlined geometries without large base separation regions. This model works best for attached boundary layers or mildly separated flows, and at subsonic speeds. In this case, I'm going to select Spilart. And notice that it automatically selected all white plus. I'm going to deselect this just to show you what our options are. For Spilart, we have the option of all white plus or low Y plus. For For K omega, we have the option of all Y plus, high Y plus, and low Y plus. The high Y plus wall treatment is a classic wall function approach, where wall shear stress, turbulent production, and turbulent dissipation are all derived from equilibrium turbulent boundary layer theory. It is assumed that the near wall cell lies within the logarithmic region of the boundary layer. Therefore, the cell centroid attached to the wall should have a Y plus greater than 30. The low Y plus wall treatment assumes that the viscous sublayer is well resolved by the mesh, and thus wall walls are not needed. It should only be used if the entire mesh is fine enough for Y plus to be approximately 1 or less. And finally, the all Y plus wall treatment is an additional hybrid wall treatment that attempts to combine high Y plus wall treatment for coarse meshes and low Y plus wall treatment for fine meshes. It is designed to give results similar to the low Y plus treatment as Y plus approaches 1 and to the high Y plus treatment for Y plus greater than 30. Note that when using the Splart turbulence model, it is recommended to integrate to the wall. However, just in case there is any part of my wing that rises above a Y plus of 1, I'll select all Y plus. And once that's done, I'll select close. Now I can see under models all the selections I just made. I'll go down to the next node, which is reference values, and here under reference pressure, I see that this value is atmospheric pressure at sea level. If my flight conditions were different, I could change this, but I'll just keep it as is for this simulation. Note that this is specified in this manner so that all other pressures listed after this will be gauge pressure using this reference pressure. That is, of course, unless it's listed as absolute pressure. Next, I'll go down to initial conditions and velocity, and I'll select constant here. I'll initialize velocity everywhere in my domain to be 45 miles per hour in the x direction, and at the end I can put in MPH and hit enter. So this completes my physics continua. I'll go ahead and right click continue again, go to new, and mesh continuum. I'll right click models, select meshing models. You always want to select the surface remesher, so I'll select that. And here under volume mesh we have the option of trimmed or polyhedral. Both polyhedral and trimmer meshes have proven successful on this class of problem. Polyhedral have the advantage of smooth growth away from the body, while trimmer meshes tend to be more efficient at putting cells in the desired areas. Due to smooth growth behavior, polyhedral are typically preferred when aerodynamic coefficients are of key importance. Polyhedral also generally work better when large sweeps and flow directions such as angle of attack and side slip are used, due to the pseudo-random orientation of the faces. If a single or small variation of flow direction is desired, a trimmer mesh with the grid lines aligned to the flow often provides the most efficient approach to getting good answers. Typical polyhedral meshes contain 2 to 20 million cells depending on the complexity of the geometry and flow field and the near wall treatment. The use of mesh expansion control is recommended with the expansion rate set between 1.05 and 1.15. Typical trimmer meshes contain 4 to 40 million cells depending on the complexity of the geometry and flow field and the near wall treatment. The volume growth rate should be set to slow or very slow in order to properly capture the near field. Here I'll select trimmer because I want to keep my cell size down since I'm running this on a laptop, and also because I'm running this at a 0-degree angle of attack. So I'll select trimmer, and then under optional models I want to select prism layer mesher. Proper resolution of the boundary layer is critical. The thickness of the prism layer should be designed such that the entire boundary layer is contained within it. Use of wall functions for K-omega SST turbulence model rather than integrating to the wall can be appropriate depending on several factors, including the desired accuracy, the relative importance of skin friction drag, the importance of transition, and the existence or importance of separation and reattachment on smooth boundaries. For integrating to the wall, 20 to 30 prism layers are typically used, with the near wall Y plus being on the order of 1. For wall functions, 5 to 8 prism layers are typically used, with the near wall Y plus being on the order of 50 to 150. After selecting prism layer mesher, I'll select close. Then I'll go to mesh 1, expand models, and select prism layer mesher. In the properties window, I want to set the minimum thickness percentage to 0.01. I'll set the layer reduction to 0, and then set the boundary march angle to 85. These settings will ensure that the prism layers on the trailing edge of the airfoil do not retract. After this, I can go to the next node down, which is reference values, and here I can specify my global mesh sizing. The upcoming mesh sizing and refinements I apply are specific to this wing under the given flow conditions. They are relatively coarse since this is being run on a laptop. Note that mesh sizing and refinements will change according to the application being simulated, the flow regime, computational resources available, and the level of fidelity needed. The refinements applied in this video should still be used, but if a higher level of fidelity is needed, then a higher level of refinement should be applied. That being said, I'll go to my first node, which is base size. This is a size that everything else references. All of the sizing controls that I see from my mesh will be a percentage of this base size. So you want this base size to be very commonly used size. What I'll do is I'll zoom into the wing, and I'll use the ruler icon up here to take a measurement across this top of the wing. Then once that's done, I'll select base size again and enter in that value. and I'll go down to maximum cell size. And in this simulation, I want the maximum cell size to remain constant throughout the interior of the domain out to the outer boundaries. So to figure out what the cell size should be, I'll go to my scene, I'll zoom out a little bit, and then I'll use my ruler icon again to measure across what the largest cell size should be out in this domain. Here I've determined it's 1 meter, so I'll go back to maximum cell size, but instead of trying to guess what this is as a percentage of base, I'll go back up to the maximum cell size and I'll change the size type from relative to base to absolute. And once I do this, I can enter in 1 meter directly into the properties. The next node down is the number of prism layers. I'll put this in as 12. Then under template growth rate, I'll set the boundary growth rate to very slow. And the last node that we have here is volumetric controls. Mesh should be refined at tips of lifting surfaces and control surfaces in order to capture vortices that are shed in these locations. So in order to do this, I can right click this, go to new, and you can see once I do this, it's asking for a shape about which it can refine within. But I haven't created this part yet, so what I'll do is I'll go back up to geometry, and under the parts node I can make some simple shape parts. Here I'll select cone, and in the scene I can move the start and end points and then specify start radius and end radius. I already know what values I want to use, so I'll go ahead and enter that now. So now I have this set the way I want it. I've also zoomed into the scene so you can see this cone that I've made. Once this is done, I'll select create and close. Now when I select volumetric control 1 under parts, I can feed that new cone part in. I'll expand mesh conditions. I'll select trimmer. I'll enable customize anisotropic refinement. Then I'll expand mesh values. I'll select trimmer and anisotropic refinement, and I'll select customize X, Y, and Z. Then I'll expand this node. For X, I'll leave this at 100%. For Y, I'll set this to 25, and for Z, I'll also set this to 25. Now that this is done, I've completed both the Mesh 1 node and the Physics 1 node under Continua. So my Continua node is complete. I'll move on to the next node, which is Regions, and under Region, I'll expand this out. The first thing I want to do under my boundary is to set my boundary type. So for instance, if I click Inlet, here you can see the default is to automatically set it to a wall. So I'll set this to velocity inlet. For outlet, I'll specify this as a pressure outlet. And then for sim, I want to set this to symmetry plane. I'll expand Inlet 1, and under Physics Conditions, Flow Direction Specification, I need to change this so that it's set to components. Once I do this, I'll expand Physics Values, and for flow direction, I need to ensure that this is coming in the positive X direction. I should mention while I'm in the inlet boundary, if you want to do an angle of attack sweep, you would need to change the flow direction specification and the angle under the inlet boundary. So I do this by selecting flow direction specification, set this to angle, and then under flow angles, you would ensure your rotation convention is correct, your reference vector is correct, and then you can change your angle of attack. When you do this, you need to change the existing trimmer refinement direction to the expected wake direction. If you expect large separation, it may be good to add another trimmer wake refinement for the whole wing, but as an isotropic refinement. If you can afford the computational resources, it would be best to use a polyhedral mesh, since it's been shown to do better with larger wakes and therefore high angles of attack. But keep in mind, this will use more RAM while meshing. I'll set this back to the way I had it. And the last thing I need to change in here is velocity magnitude. I'll put this in as 45 miles per hour. And as far as physics go, that completes the setup for all of my boundaries. For the outlet, it's 0 pascals by default, which is fine. In regards to boundary and edge refinement, first I want to go to wing tip and refine this. So I'll expand mesh conditions, customize surface size. I'll enable this. Under mesh values, I'll specify the target and minimum size to be 12.5% of my base size. In general, mesh should be refined around the leading and trailing edges of lifting surfaces, control surfaces, and other protrusions. So to do this, I'll expand the feature curves node and then set the leading and trailing edges all to 12.5% of my base size. If I condense my feature curves and boundaries back down, I'll set up a trimmer wake refinement for the wake behind this wing. So to do that, I'll expand mesh values, right-click trimmer wake refinement, and select new. Under boundaries feature curves, I'll feed in the trailing edge, and then select OK. I want to apply this 2 chord lengths downstream. I'll keep the direction as X, and then I want to enable customize anisotropic refinement. Once I do that, I'll select the node below, and I'll enable this for X and Y. Then I'll expand this. For X, I'll set this as 50% of my base size, and then for Y, I'll set this as 12.5% of my base size. Now as a final step, I do need to coarsen the mesh at the inlet, outlet, and symmetry boundaries, since they will by default accept the global mesh settings. And remember, in the global mesh settings, the base size was adjusted for the sizing on the wing. So to coarsen those boundaries, I'll expand the boundaries node. I'll select outlet, symmetry, and inlet. I'll right click, select edit. I'll expand mesh conditions. I'll enable customize surface size, expand mesh values, and remember before we determined that 1 meter was the size that we're going to use. So I'll change this from relative to base to absolute, and then I'll expand each one of these nodes and put in 1 meter. Then select close. After this, I'll select mesh. My mesh is complete. I see that it took about 142 seconds, or about 2.4 minutes, and it produced about 1.9 million cells. If I create a mesh scene, I can view my new mesh. Here in the scene, you can see the large sizing we applied on the outer domain. You can see the template growth rate slowly steps up the sizing of the grid as we move away from the wing. If I zoom in, you can see the trimmer wake refinement here. Here you can see the prism layers. If I hide this, you can also see the leading and trailing edge refinement. If I want to view the mesh on the interior of this volume, I would need to create a cut plane section and put that in this scene. I would do this in the Derived Parts node, but first I'm going to condense all of my nodes here in this scene just to clean up my view a little bit. Then I can go to Derived Parts, right click, New Part, Section, and Plane. In this view I can see that the cut plane section would be put in a location that I actually need it to be in. However, if I wanted to change the cut plane section to a specific location in the Z-axis, what I could do is I could use my mouse pointer to point to the location I want the cut plane section to be, press period on the keyboard, and in the output window I'd get this cell probe that shows me the position of that mouse pointer. So if I wanted to change it to that location, I could copy this value here and then paste it in up here in the Z origin. Like I said, there's nothing I particularly want to change about this cut plane section, so I'll just add it into the existing mesh displayer, select create, and close. Then after closing, you can see in the scene how this has been added so that we can see the mesh on the interior of the domain. The next node down after Derived Parts is solvers. In this case there's nothing to really change, so I'll move down to stopping criteria. Here under maximum steps, I want to change the maximum steps to 300. And just remember, the maximum number of steps you may need for your simulation will change depending on the application and depending on your grid as well. For this particular simulation with this grid and these flow conditions, I've seen it converge within 300 iterations. I'll skip down to the reports node. Here I'll begin by creating a frontal area report. Then once I select this, I want to ensure my normal is in Y, and then my view up can be in X. Then under parts, I want to feed in all the boundaries of my wing. Once this is done, I can right-click frontal area and select Run Report. Then in the output window, if I scroll down, I can see the total area projected in the positive Y direction. After this, I'll right-click Reports again, go to New Report, and Force Coefficient. Here I'll name this CL for Coefficient of Lift. The direction will be set in Y. The reference density should be 1.225, and the reference velocity should be 45 miles per hour. Then I'll scroll down. Under Reference Area, I want to copy this and paste this in for this report. Then for parts, I want to apply everything on my wing. And then select OK. Then I can go up, drag and drop CL onto the reports node, and this makes a copy of it. Then I can rename this CD. Then I'll set the direction in X. I'll right click reports again, new report, and force. Here I'll keep the direction in X, the reference pressure is 0, and on the parts listing, I want to apply the wing again. I can rename this drag, or just D, and I'll drag and drop this on reports, rename this L, and again I'll just change the direction to be in Y. I'll right click reports one final time, new report, expression. Then here under definition, I'll put in L report divided by D report, and then select OK. Then I can rename this report L divided by D. And this of course will be our lift to drag ratio report. As you saw earlier, I can right click each one of these reports and select Run Report, and in the output window it'll give me the current value. Instead of doing this, I want to create a plot for each one of these reports so that it will plot the value of that report for every iteration. This way I can monitor convergence and the values for each one of those reports. To do this, I'll select all the reports I want to create a plot for. Right click, select Create Monitor and Plot from Report, and here I'll select multiple plots. I'll go ahead and close the open scene, save this, and then select the Run icon. I'll fast forward through the running of the simulation. It took about 2 hours and 40 minutes to complete with just one processor. I also tested this on 2 processors and it took about 50 minutes. As I mentioned before, I'm running this on a laptop. The computer specifications for this laptop can be seen here. Always remember that as you add more processors, the time per iteration will go down, and the overall time it will take to complete the simulation will go down as well. To monitor the convergence of the simulation, you should take a look at the residuals, along with plots of forces and moments. So in this residuals plot, you can see how the residuals go down 2 to 3 orders of magnitude, then flatline. If I open up my lift to drag monitor plot, and then zoom in using the wheel on my mouse, you can also see here that this is converged to a value. We should look for these plots to remain or oscillate about some value across a number of iterations. Now as a final step, I'll create an XY plot of coefficient of pressure versus chord length position. Then after that, I'll create 5 scenes so we can visually look at our results. So to do this, first I'll right click Plots, New Plot, XY. Now under the parts listing, I need to feed in a curve that resides on the airfoil surface at a particular point in the span of the wing. Now if you remember before, I created a cut plane section to look at the mesh on the interior of our domain. This is good, but the cut plane section was applied to the region, which means that it's going to look at everything inside the region. If we applied that same cut plane section just to the wing boundaries, we would get the curve that we're looking for. So to do this, I'm going to expand Derived Parts, make a copy of this cut plane section. I'll rename this Curve, and under the parts listing, I want to feed in the boundaries of my wing. Once this is done, I can go back to XY plot 1 and feed this new derived part in. Then I can expand XY plot 1, I'll expand X type. Here you can see its position in X, which is fine. Under Y types, I'll expand this. For scalar, I want to feed in pressure coefficient, scroll down and select this. And once this is done, you can see that our plot populates. Next, I'll scroll down and begin creating my scenes. I'll begin by right-clicking Scenes, select New Scene, and Scalar. Now I could manage everything to do with this scene in the Scenes node itself. Here I could expand Scalar Scene 1, and then expand Displayers and work with everything here, but it's oftentimes easier to just go up to the Scene Plot tab and manage everything here. First thing I'll do is right-click Outline 1 and delete this. And under Scalar 1, for parts, I want to feed in the boundaries of my wing. And then select OK. I'll reset my view using the R key on my keyboard. I'll reorient this view. And in the next node down, for scalar field, I'll put in pressure. Now if you want to give the scene a more smooth effect, I could choose Scalar 1, and then under Contour Style, I can choose Smooth Filled. I'll go back to the Simulation tab, and I'll rename the scene Scalar Surface Pressure. Then I can drag and drop this scene onto the Scenes node, which will make a copy of this scene. I'll rename this Scalar Surface Wall Y Plus. When I made a copy of the scene, you can see that it opened this up, and I could go to the Scene Plot tab and change the field to be Wall Y Plus, or I can actually do it here by right-clicking and then scrolling down to Wall Y Plus. I'll copy the scene by dragging and dropping onto the Scenes node. I'll rename the scene Scalar Cut Plane. I'll go to the Scene Plot tab, and under Scalar 1 for parts, I want to put in my derived cut plane section that I made earlier. And then select OK. Then under Scalar Field, for function, I'll put in velocity magnitude. Then here in the scene, I can press T on the keyboard. That will give me a top view, and then I can zoom in. I'll go back to the Simulation tab, scroll back down to Scenes. I'll right-click Scenes, New Scene, and Geometry. Under Scene Plot, I'll delete Outline 1. And then under Geometry 1 for parts, I want to just apply this to the wing. And then select OK. Then I'll reset my view, scroll in, and reorient this view. Then I'll go to the Simulation tab, I'll scroll up to Derived Parts, right-click Derived Parts, New Part, and select Streamline. Then under the Seed mode, I'll put this in as Line Seed, and if I display tool, you can see that I can drag and drop the start and end points of this line. I already know what values I want to put in for point 1 and point 2, so I'll go ahead and put these in now. Once this is done, I'll scroll out a little bit so you can see the line position. I'll ensure under display, I select new streamline displayer, then create. Then I'll create one more of these and add it to the existing scene. And I'll do this by changing the Y position. Once this is done, under display, I'll add it to the existing streamline displayer. I'll select this and select create. Then I'll select close. I'll go back to the scene plot tab. Now you can see this new section stream 1 displayer. I'll expand this, and when I select section stream 1 under mode, you can see this is set to lines. Personally, I like tubes, so I'll change this over to tubes. After that, under scalar field, I can change this to velocity magnitude. And as one final touch under animations, if I turn this on to tracers, you can then select play above and see the animation. You can also go into the scene and rotate this. If these tubes are looking a little bit thick, I can go back to section stream 1 and narrow this down. I'll go ahead and select stop above, and I'll create one final scene. I'll go to simulation, scroll back down, right click scenes, new, and vector. Again, I'll go to the scene plot tab, I'll delete outline 1, and under vector 1, under parts, I'll feed in the wing boundaries, and then select OK. Under vector field, for the function, I'll put in wall shear stress. Go to my scene and reset the view so I can see my wing. And here in the scene you can see these as individual vector glyphs. To change this, I'll go to vector 1, and under display mode, I'll change this to line interval convolution. Now if I wanted to change the degree of dihedral of this wing and change the overall wing length, I'll go back to my simulation tab, I'll scroll up to geometry, expand this, expand 3D CAD model 1, and under design parameters, I'll change 8, 9, and 10 position. Once this is done, if I expand the parts level, you can see how these parts need to be updated. To update these parts and re-execute the subtract operation, I'll expand the operations node, right-click subtract, and select execute. And because everything is linked together from 3D CAD to parts and operations, when I execute this, it will update the CAD, then the parts, and it will re-execute the subtract. Now all I need to do is go to solution, clear solution, select OK. I'll select mesh, since we need to develop a new mesh for our new geometry. And once our mesh is complete, you can see how this updated in the scene. If I scroll back down in my output window, you can see that it took about 292 seconds, or about 4.8 minutes, and it developed about 2.5 million cells. Before running this, I'll right-click up here and select Close All Documents. And the reason why I did this is because I don't want it to be rendering the scenes while I'm trying to run the simulation. After this, I'll go ahead and select Run. Once the simulation has completed its run, I can go back down to my plots, right-click Plots, and select Open All Plots. And I can review these for both convergence and also to see how the performance of this wing has changed. To visually see how the results have changed, I can go to Scenes, right-click, and select Open All Scenes. Here I can review the new mesh that was produced for this wing, values of pressure on my wing, wall shear stress, and the velocity magnitude on the cut plane section I had created earlier.